All right. So unfortunately, we had a long time between last class and this class, right? Because of that holiday. So we'll start off with some review just to get us in the right place so we remember what's happening. Actually, I'm going to make sure this audio is recording. I've heard it's had issues. Okay, it looks like it's recording, hopefully. All right, so last week, 2 weeks ago, whatever it was, time's weird, we talked about multiple gates and how bad I am at drawing them. Right, so we have an AND gate, an OR gate. Does anyone remember what this one is? Looks like an OR gate. NOR gate. Here's our NAND gate, right? So these bubbles mean not. So we can explicitly write them out by putting in an inverter, right? So we have AND, OR, NOR, NAND, inverter. Now, these operations are kind of self-explanatory, right? So in the case of an AND gate, if A and B are true, and when we say true, we mean 1 or high, right? So like in our lab, if we saw a 1, it meant 5 volts. So in our labs, 5 volts is 1 on high true, right? We have lots of words that mean the same thing. The OR gate, if A or B is true, then C is true. The NOR gate has the same property as the OR gate, just inverted. Now, we express this, the operations, through something called a truth table, right? The truth table is, we take A, we have a B, and we count up in binary, right? Now, ascending numbers is useful, and it just says something like, if I want to have an AND, the only time the AND is true is when they're both true, or 1. Okay, go back in those zeros, boom, and. We can then kind of build out this truth table and say, what does the NAND do? Well, the NAND is the same as the AND, just the opposite, right? So instead of 0, 0, 0, 1, 1, 0, 0, or sorry, 1, 1, 1, 0, NAND, it's just the opposite. Okay, so something that then gets more useful as well is we have alternative forms, and I think I put some of these on the homework, right, of how to draw and rather NAND and NOR. These are most important ones. So NOR can be drawn using an AND gate, like so. These are equivalent. Similarly, this is a NAND gate, NOR, NAND. Okay, equivalencies, we kind of have that in the lab. All right, and then we went on and we started talking about De Morgan's theorem, right? Now, De Morgan's is kind of tricky, but it is an important operation because it allows us to invert functions, but it also allows us to simplify otherwise complicated algebraic expressions for Boolean operations. So let's go ahead and say that I have a function like so. Now, I could just sit down and draw this as a circuit, right? The way that I would do it is I would identify what is my output gate. the last gate that I need to do? Well, in this case, it's an AND gate because I'm ANDing this term, A or B, and not, remember that's what the bars mean, not, invert, A and not B, or not A and B. Okay, that might be a little bit tricky to draw if you're not experienced. So what we want to use is De Morgan's theorem. So what we're going to be doing, certainly on our exam and our homeworks and our labs, is simplifying algebra, Boolean algebra. Slightly different rules in that we don't have subtraction or division, but addition and multiplication work the same. But De Morgan's, what does De Morgan's tell us? De Morgan's says we take the terms under the not, we change ors to ands, and we invert the terms. Now we have to be careful because when I say terms here, I don't mean A and B, I mean A and B and not A and B first. So the first step in De Morgan's keeps these AND gates intact. What it inverts is I get A, B bar, bar. Right, I haven't changed the A and not B, I've changed the whole term of the multiplication. But this OR gate becomes an AND. We stick with that guy, put a bar over it. This keeps the parentheses. Okay, we're not done because we still have a term. We have a multiplication, multiple inputs that are underneath the not. We just repeat the process. And we'll do De Morgan's separately on each of these. So the A, oops, I don't want this to get too cluttered. Okay, so the A gets inverted, the AND gets turned to an OR, and the B bar gets inverted. What is not B? Just B, right? This AND stays intact because it wasn't part of the bar that we're dealing with. And now we're going to move on. I'll keep that AND, right? To the next one. A bar bar is just A. B bar. Great. Is it likely that we can simplify this one further? Right? I mean, we don't have that many terms. It's probable that we can solve it. Sometimes the only way to do it is to try. What do we see that looks like it would simplify? What operations we can do to get us into position that we can simplify this? Well, we know we can distribute, right? I can FOIL it, first, outside, inside, last, yada, yada, yada. And what I like is that in all of these terms, I mean, if I multiply A bar and A, right, that's my first, that cancels, right? A bar and A is what? I'll write this out explicitly. What is that equal to? So if A is 0 and A bar is then 1, the only other situation is 1 and 0, right? Can this and ever be true? Right, so what is this equal to? 0, because it can never be true. Okay, so I like that because we have an A bar here and a B and a B bar. It's kind of clear once you understand what we're trying to simplify that they're going to cancel in a nice and orderly way. So let's just start foiling. A bar A, and I'm going to do the AB, right? Sorry, AB bar first, outside, inside, last. Okay, well, this is fortunate because if I have 0, I have 0, I'm left with this. What does this do? What do we see here? Yes. Does everyone see why? I'll do it, but right, if I factor out the A, then I just get B bar or B, which this must always be true. Because if B is 0, the other one's 1, and vice versa. Great, so we're left with A. Okay, now we have A and A or B. I can multiply this through. A and A or A and B. Oh, sorry. I said it right and wrote it wrong. Well, that's interesting. What's A and A?
Should there be another A bar
Oh, did I lose one?
on the second term? Or am I just looking?
No, it's entirely possible I screwed up. Good question. Let's walk through. A bar A, A bar B bar. Okay, so I did do that simplification wrong. Good catch. It still simplifies though. And I'm going to drop these zeros so that it looks a little cleaner. Sorry, A bar A, A bar B bar, A B, B bar B bar. Okay, that one we fixed now. Okay, let's bring this down so it's a little bit clearer. All right, there is probably, I don't see any obvious simplifications here in this one. So let's just go ahead and FOIL it out again, right? So now I'm getting A bar, B bar, or this is, sorry, my brain's a little off. This one, that one, A bar, shoot. I'm gonna start over because I've let myself get distracted. Okay, A bar, B bar, A bar, B bar, B, ABA, so AAB is another way of writing that, or ABB. Okay, now we can start seeing some of the common issues. We have an A and not A in one AND gate. Again, never can be true. It doesn't matter that there are other terms in this one. A bar and A can never both be true, so that AND goes away. Same issue here, B bar and B can never be true. A and B, A's drop. Because if A is true, A is true. It's repetitive and boring. Or, well, B's drop. Now we have AB or AB, which they're the same. One of them drops. Now, I know watching me is one thing and doing is another, so I'm going to throw up another example here. I'll just write it to the side so you can kind of peek back at the other one. And I'll have you guys work through this so that you feel like you get it. And this one has 3 variables, so it's fun. Okay, yeah. So go ahead and take a moment to try and solve this one, reduce it down. And it reduces pretty far. Okay, did we all get at least this far? I think I did that right. Okay, what do I do next? What do we see?
Well, the not A and B, and the not A, not A, B, and C can just be simplified to not A, B, C.
Yes. Yeah, we're just combining like and like there. They're repeated, we don't need them. Good one. What else do we see now? Someone else. Look, you're looking for like terms or inverted terms. These are the kinds of things that cancel, right? So we have an interesting one here that maybe we can do with, because I have an A bar in this term and an A bar in that term. So I have something like A bar times C bar or BC. Combining this term and that term, I think, right? Yeah, because I just pulled out an A bar. This one, does that one simplify? It does. What does it simplify to? Right, this is that rule 16A or whatever it is in the book. Does anyone remember what that is?
B or C.
So A bar and B or C. Now we got to be careful. We'll want to look that up because I don't have this one memorized because it's tricky. I don't expect you to have it memorized on the test either. You will have your book. You can look it up. Right, the general form is if you have X or X and Y, or X not and Y, it equals something, right? So do I have to look this up? Yeah, is equal to X or Y. So here we have X or X bar Y. Here it's flipped, actually. We have C bar or CB. So our X is C bar. Well, that's a tricky one. And that's why it's worth looking up, is because that's an easy mistake to make. And then we have A bar or B. And I can drop these parentheses now at this point and say or. And now I can pull this back if I want to, or B, or A bar B, or a C. All right, now here's where the logic part comes into this. Here I have an A bar. Here I have an A bar. Can this one ever be true unless this one is true? You could also do this by factoring out the A bar and seeing that it was what A bar and 1 or B, right? And 1 or B is 1, which is another way of saying we don't need that. And there's no way we can simplify this because it's got a C stuck in it. Although we do have this, 16A again, right? Same theorem. X and X or not X, Y comes down to, well, our X is A bar. So I have A bar or B or C.
Actually, like A bar, C bar though.
Good catch. There is a C bar here. I actually kind of think that I screwed something up somewhere because in my head, I think they all have bars. Be aware that I may have made a mistake somewhere along the ways. I lost a B bar. I don't see how though. Maybe I wrote something down wrong. Anyway, that's the general process that you're shooting for in simplification. It requires practice. That's why I keep giving you homework that has this in it. It is worth reviewing because De Morgan's is tricky and that 16A is tricky. So I found good examples that used both, right? Yeah. 33. It starts on 32. So they have like single variable formulas, 2 and 3 variable properties, and they have like duality and a few others. There'll be a few more homework assignments. I've gone kind of light at the beginning of the semester because the schedule's weird, but it'll ramp up a little bit as we get more practice in. Okay. Next topic. So the next thing that we want to talk about, and I can't remember with you guys if I just alluded to doing this or if we started it. Fortunately, it's easy. What we want is to be able to convert circuits to something called universal gates. The two universal gates that we really care about for digital design are NAND gates and NOR gates. Now we'll actually hopefully get into why we like these gates in this lecture. But the main idea is that you can make any circuit out of a NAND gate and any circuit out of just NOR gates. Either one is just fine. And if you're making circuits that use a bunch of NAND gates, it's cheaper than making a circuit that uses NAND and NOR and OR, right? It's just scalability. We like using a bunch of the same thing, just like in lab, when we built it by hand, it's easier to use one chip that has a bunch of NAND gates on it than it would have like 4 chips, 1 chip for each type of gate. It's cost and efficiency. So how do we take a circuit and turn it into NAND or NOR gates? Well, fortunately, it's easy. So if you want NAND gates, you start with an output gate of an OR. If you want NOR gates, you start with an output gate of an AND gate. All right, so we have an AND gate output here. And we want to turn this into NOR. All right, so what do? We use this idea of not. So, and we use this alternative drawings of circuits. We know that this is a NOR gate, right? This is just another way of drawing NOR. But this is no longer the same function. How do I keep it the same function? I add, well, 2 nots, not, right? Nothing's changed now. So another way, these knots are just inverters, right? But what I want to capitalize on this idea is, if you recall, this is a product of sums expression. This is why we like product of sums and sum of products, right? Because what happens now is I can, what I call bubble pushing, I can push these 2 bubbles that I had to create to keep the circuit the same, the function the same, and I can just push them back along this wire until I run into the OR gate. And what happens then, I get a bubble here and a bubble here. Well, you can clearly see that I've done not, so the circuit's the same. And that's a NOR gate, that's a NOR gate. Done. The reverse works for an OR output gate to make NAND gates, which is an example that you're about to do as soon as I draw a circuit for you to do. Okay, so sometimes in more advanced circuits, you're going to have to throw in an inverter. Now, as a rule, if I tell you to design a circuit that says use only NAND gates or use only NOR gates, I'm not going to fault you for using an inverter. Because it turns out making inverters out of NAND gates or NOR gates is really easy, like trivially easy. So if you just leave the inverter, it's fine. If you end up in a situation where you have to throw in an extra inverter, which can happen, it's okay. So go ahead and take a moment and try to use this idea of bubble pushing, the not idea, to convert this circuit into NAND gates. Starting with the output gate. Always move right to left in this method. Okay, so I'll walk through this. I just wrote the answer, but right? So all I did on the first one is virtually identical. I just created the two inversions to make that a NAND gate, pushed two extra bubbles down, those immediately turned into NAND gates. Fortunately for us, the next stage is just repeat. I don't have any stray inversions here that I have to worry about. So I can just throw two bubbles here, right? No change between this connection. That's nice. Then one bubble here's got to get pushed down. But I end up, and I'll start from here, right? So this is a circuit where this is not true anymore, right? I've got a floating bubble. What is the floating bubble? As I mentioned before, it's just an inverter. So I'll draw it as a buffer to start, right? Buffers don't do anything. They keep it, if the input is 1, the output is 1. Now I have something to run into with the bubble. Boom, done. Does everyone get that? Okay. So that one, I'm not gonna spend too much time on it. It's kind of easy. It's just don't lose track of bubbles when you have to make an extra one. Now, it is possible, and I always screw this one up, to go the other way, and you'll end up with the opposite kind of gate usually. I don't really like it. Let's see if we can pull it off. I wouldn't worry too much about this because you're almost always going to start from either a sum of products or a product of sums and then be able to just do this. So if I wanted to turn this circuit into, rather than NAND, NOR, it's a little bit more challenging. So what does a NOR look like? Well, bubble, bubble. But I have a problem, right? So I have to go A bar, B bar. That's a NOR gate, I'm okay. This guy, at a bubble, he's a NOR gate. But I need to push another bubble up here, boom. Need a bubble here, but to do that, I need a D bar. So the bars are just another way of saying an inverter, right? This is functionally equivalent to saying an inverter. I'm just inverting the input. Okay, same thing happens here. Bubble, bubble, not. This guy, bubble. Well, that's an issue, right? Because I just changed the circuit, L bar. Or L. So it's doable from left to right to get, you'll tend to get the opposite type of gate. It is easier to go right to left. And you'll learn when we get, maybe next week, and if not the week after, we're gonna get to a design tool we call Carnot maps, I don't know how it's pronounced, or K-maps for short, because that's what everyone uses. Is a design tool, and it makes it really easy to choose which circuit architecture you get. But we'll get there. Okay, but speaking of design, let's talk about how do we design circuits? Because designing circuits really is just story problem, right? Is I want you to achieve X. Are we good if I erase this? Okay. I would say, I would like you to design me the circuit that does X, and you will figure out how to turn those words into a circuit. So in the book, they have an example that I'm going to go through that is a really good example because we've all kind of experienced it, right? Let's say that you have a house, and in your house you have a living room. This living room has 3 light switches. The light starts off with all light switches in the down position, the off position. Now, I may make some mistakes because the down position is off, but you can have different situations depending on the light switches are on, right? The status of the light is different than the status of the switches. I'll get to why. Okay, 3 switches, light starts off, all switches start down. The light turns on if I click up any switch. Any one of those switches, the light turns on. If I flick up the next switch, it goes back off, right? Because when you go in that room, you want to, when you flick the switch, it to do the opposite of whatever it's currently doing. Okay, then if I flick up the 3rd switch, the light goes back off, right? So it goes up is on, back on. Up is on, 2 is off, 3 is back on. Now, design the circuit. Now, I won't make you do this on your own. What I want you to realize is there are a couple ways to do this. The first way with simple circuits is to think through it. Because we're looking for F, we'll call it F, right? What is the situation in which F is on? That's what this equation means when I write F equals, right? Because F is either going to be true or false. When is it true? What are the conditions? When 1 is up, or all 3 are up. So let's call our switches A, B, and C. So if I have A, it's on, or if I have B, it's on, or if I have C, it's on, or if I have A and B and C. Okay, cool. Now, there's a possibility a lot of times when you first do this type of strategy that you're going to end up in a situation where things are redundant, right? We may be able to simplify. Shoot, this isn't quite true. I did make a mistake, and this is good. So it's not true if just A. I actually need to be more explicit because I care what the other switches are doing. There we go. So now if I have A, but not B and not C, or B, but not A or C but not A or B, or all of them. There we go. I could look at that and see it wasn't going to simplify and I got confused. Okay. So that's probably actually a good mistake that I just made, because you can kind of see how easy it is to fall into that thinking, aha, I did it. Now, the better way to do this, the more thorough way to do this, will prevent you from doing this and would make it very obvious very quickly, is our good friend, the truth table. It is not just good for gates, it is good for everything. So if I do A, B, C, and F, and again, I have this little trick that I do where I just go column by column. And then, so the first column alternates every 1, the second one is every 2, and the next one is every 4. And now we have the concept that I mentioned last time, and I don't expect that it stuck, of min terms. Now recall that a min term is a statement that is true for only one line of the truth table. Okay, so what does that mean? Well, I know that it's true from the definition when one of them is on. 1, 1, 1, or when all of them are on. If it's not one of those, it's off. And now I can represent this with min terms, where this min term must account for all of the variables, and then I just write what they're doing. Not A, not B, is C. And then I repeat. Okay. So those are called min terms. So it seems like a lot of work if they're this predictable to keep using them. So we have a way of writing these expressions in terms of min terms that is shorthand. One way to do that is we say something like F is equal to min term, and there's 0 indexed. This is important. So this is min term 0. That would be M0, but we don't have M0. What we have is, well, actually, I'll write this to the side. 1, 7. What we have is 1, 2, 4, 7. Okay, that's shorter, but we can do better. We can actually write this as the sum of mins 1, 2, 4, 7. So I can ask you the question, please simplify for me this. You may have to go back and draw out the truth table to remember what that means. That's okay, it's not really a problem. But this is just another way, a shorter way of saying this. It is more effective the more variables you have. You can imagine if you had 8 variables, how long that expression could get, as opposed to 1, 2, 4, 7, 13, and 20, or whatever, right? Much easier. Okay. That being said, I have this function. We want to simplify this function. You've built a circuit. You want to do it as cheaply as possible. Okay, this has, well, 5 gates, right? It has 4 3-input AND gates and 1 OR gate is the output. Does everyone see that? Okay. So now we want to start looking for where can we simplify? What can we do to make this easier? And what we can start doing is looking for like terms. We have stuff we have like lots of individual repeats. We have B bar, B bar, B, right? This one can actually be kind of frustrating in terms of where to start. And it's actually kind of true that you can find yourself minimal logic that is different than someone else's and they're equally minimal. That can happen, by the way. Okay. So what if we just start somewhere and say something like, I'm going to start here and just pull out this C bar. I don't know if I like that one. What's funny is I'm actually not sure this one simplifies very far. Does anyone see anything that's actually going to help us get to where we want to go?
Thinking where we have I mean, it's either, well, it's either, I mean, for some of these statements, it's either, I mean, we could use exclusive ors, but
Yes, yes, you can. So
that's,
once you become kind of enveloped in this world, you'll recognize this is what's called an XOR gate, exclusive OR. If you recall, is drawn like this, where the truth table for this one is if A or B is true, then C is true, but not if A and B are true, right? That's why it's exclusively A or B. That gate, unfortunately, doesn't do us anything towards getting towards like a minimal circuit. And I actually don't see anything in this circuit that I could simplify. What I'm really looking for is two terms that share, man, I really need to figure out what the proper vocabulary is. Two of these multiplications, two of these AND gates that share two inputs. So if I had an A, B bar somewhere else, that would be a good sign that it's going to simplify. Now, you don't require that. There are other operations like that 16A simplification, but I don't see anything that's going to simplify in this one in any meaningful way. So let's go ahead, build the circuit. Well, we already know that it's going to have an OR gate, and it's going to have three input AND gates. Where this would, I would just label A, B bar, C bar, etc. Right? I'm not going to label all those because it'll take time. Now this is, when using minterms, the exact circuit that you would end up with because it's a product of sums. You always get a product of sums, sorry, sum of product. You always get a sum of products when dealing with minterms. Always. Which means that turning this into universal gates is as easy as bubble, 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 done. I will ask you, that will be an exam question. 100% promise. I mean, not this exact formula, but you know, process-wise, where I will give you a story problem. You will write down the truth table, you'll get the minterms, you'll build the circuit, and then turn it into universal gates. It's an exam problem. Okay. I'm debating whether to introduce max terms yet or not. So max terms are everything that isn't the minterms, right? It's when it's 0. So max terms have this nice property that they produce product of sums, aka NOR gates. Now, they're a little bit trickier, but you do essentially the same thing, right? So product of sums. This is sum of products. What we're going to do is we're going to create, so instead of creating products, we're going to create sums from these variables. So here's mins. Let's build maxes. Maxes can be used also to describe something. The same shorthand kind of terminology where I say F is equal to max terms. You use this little house symbol here, and we go ahead and say, well, it's 0, 3, 5, and 6. Now, these are a little bit ungainly because instead of just ABC, it takes the form of A or B or C. And we do the opposite of what it says in the truth table. So this is the max term for 0. Here, C, and here, A or B. So what I like to do is I fill out all of the A, B's, or C's and then figure out which ones are supposed to be inverted. In this case, it's the ones that have 1s on them. Okay, now let's go ahead and do something useful and interesting as far as learning goes, right? This is one of those kind of mathematical proofs to make sure you're sane, to make sure you're right. What can we do? Well, we can have some kind of fun by just saying F bar. Okay, so that means this whole thing becomes F bar. All right, what do we do when a whole bunch of things are barred?
Use De Morgan's theorem.
We use De Morgan's theorem. Okay, so we have this that just becomes or, and then knotted, right? Which I don't want to write down because now I have, well, I'll write the first one. Okay. And then I have okay, so now we have something interesting, right? This is the min term if this were 0, right? So this is the min term for not F. And I can go ahead and build that out. Okay. If anyone's confused on that, let me know. This one struggled to stick with me when I was a student, so I have a particular weak spot on that one. All right. So So now we can go ahead and move on to, right, you see what I'm doing, right? I'm showing you how to build one, and then I'm gonna have you do an example. I want you to make sure you get these examples in class, so if you get stuck, you can ask. Next example. There is a circuit called a multiplexer, or a mux, M-U-X. Most of the time I will say mux, but it is also multiplexer. Make sure you know this. Now what a mux does is it has a circuit symbol like so. Okay, and what this does is it connects C, the output, to either A or B, such that if select is 0, then C is equal to A. If S is 1, then C is equal to B. So what I want you to do is go ahead, and I'm going to relabel this. I don't need to change the truth table, right, other than the labeling. And I'm going to group all of the S's together because that tends to be helpful for this. And then it doesn't really matter. 0. Okay. So using this truth table for me, please go ahead and create the expression. Design me the expression to build the circuit. And if you finish that, go so far as to build me the circuit. The way I would ask this in exam is I would tell you there's a mux. Based on the select signal, C is connected to either A or B. Build me a circuit that uses only universal gates. That's a legitimate question. I could ask you on an exam. Are you taking this class, or have you just had experience?
Yeah, I had a little bit of a crash course. Logic circuits stuff.
Yeah. This is a nice smooth introduction, so if you've already had some, it's
Yeah.
real easy. Trying to look past you to make sure they're following too. You done? Okay, so if S is 0, what is the value of C? So it's A, right? What I defined it as. So if S is 0, then C is equal to A. So S is 0, A is 0. What is C? Right, so this is like the prime number problem that I used last 2 weeks ago, whatever, which is where you're just looking for the lines in the columns and seeing what they evaluate to. So this one is saying that, well, S is 0, and I defined saying that if S is 0, then C is A, okay? So I guess I could probably write this as C since I did that this way. Ooh, yeah. So S is 0, therefore C is equal to A. A is 0. Well, this is easy now. Now that I've got that first line, because I can say as long as S is 0, we just mirror A. Right? I've just written down the A column for the whole S is 0. For S is 1, I'm now selecting. So I should say that. S is select. So you will see me write it as select S or SEL is really common nomenclature for that port. Okay, so once S is 1, I just mirror what's happening in B. Boom, done. Okay, and then we would go about and we would write out the min terms, right? Actually, let me look at how much I have to cover today and see if I want to have you guys do that whole thing. Does anyone feel like they need the practice of taking it from the truth table all the way to the universal gates, or do you think you could all do that right now? Who thinks they could do that right now? So not quite everyone. Let's go ahead and do it then. So take a moment. Your next step is write the min terms, which are the lines where it's 1. Then turn that into a circuit that is going to have an output gate of OR, and then turn that into universal gates. Go through the process of it. hopefully you were able to get to that min-term expression. And now I've highlighted for you the things that we're looking for in simplification, right? This is kind of nice, because now I have two things that are similar, two inputs that are similar. I have not A, B in two places, which means that that simplifies to not A, B, and C bar or C. Similarly, I have A and C in common. Does that make sense for everyone to this part? Really, guys, if you're stuck or confused on this, if you aren't following, please speak up. I mean, it's not a bad thing. People are retaking this class. People have been exposed to digital logic before. It's not a bad thing to be confused, especially because electrical engineering, we kind of have this idea, this stereotype, that people end up falling into either analog or digital designers because digital is weird. It can be hard to wrap your head around. So if you're stuck, please let me know because I can get you there. It is teachable. I've never known someone that can't get this. So if you're stuck, let me know, use office hours, speak up in class. Don't be embarrassed. You see me make mistakes, I'm not gonna judge you. I'm not perfect and I have a PhD, guys, like I'll still screw it up. Okay, and from here we have a really easy circuit. Sorry, I did this really dumb. C is supposed to be select, isn't it? I really screwed this one up. Sorry, my notations were bad. I used A, B, C, but A is really select, and B is really A. So if you were really confused about how I did that, I fully understand. Speak up. So I said A is select, so this is really S bar. I said B is really A, S, and B. Okay, I fixed it. Now this makes more sense. I was looking at it, I was like, that doesn't make sense. So I have to have either select or not select, right? And then I just AND A and B with their appropriate term. Now I have a mux. Now you will see another form of this truth table, which is just a really simplified version that means the same thing, where they just say, the only thing I care about is select, and the select is either 0 or 1, and the output is A or B. Okay, so what that means is I have put the variables into the output column of the truth table. Don't get confused when you see that. This is all it means, is that depending on select, I just choose one of these other variables. It's a condensed truth table for a mux. Great. We're now going to go ahead and move on to the next topic because I'm sure your brains aren't blowing up yet and you're just fine. We okay if I erase? So this next subject is mostly about so you understand what's happening inside of these gates. So we've addressed the idea of switches, right? So a switch just looks like this on a schematic, and it usually has an arrow, which says that if I have this select, I'll use S here as well. If select is 0, it is open. If select is 1, it closes. So we also have this technology, the foundation of everything that our modern world is built on, which is called FETs. Now, there are two different types that we in this class concern ourselves with. One of them is called an N-type or NMOS, and the other one is a P-type or PMOS. Now, in the analog world, which we don't care about in this class, these have a different function. In this class, in the digital world, these are just switches. Now, we draw them like so. Now, you'll see variations on this one, on the NMOS or PMOS. This is the simplest way to draw them, and that's all I want you to concern yourself with. You'll see something like this fairly often. I don't want you to concern yourself with like device physics yet. That comes later down the road of this degree. But basically what happens is that if you apply a voltage at this gate, here we have the gate, G for gate, then what we can do is say that the source and drain, right? You have a current source and then somewhere for it to go, like water, you have a water source and a drain for it to go down. Okay, so you have a source and drain. When you apply a on voltage at the gate, it functions like a valve. It opens up the switch so that current can flow through. So with an NMOS, when I apply a 1, the switch closes and turns the circuit on. A PMOS, see how it has a little bubble? It's just the opposite. When I apply a 1, it opens, right? That's all these devices are doing as far as we care in this class. They're doing way more than that. They have tons of physics and it'll melt your brains. But this is the fundamental idea is switches. We like switches. When you combine them together, when you have NMOS and PMOS devices in one chip, you end up with what we call CMOS. All this is complementary MOSFETs. C is complementary. A MOS being a specific type of FET. There are other kinds of FETs. But we won't get into those, you'll learn later. So, keeping it simple, you have NMOS, PMOS. These switches turn closed when you give it a 1. These open when you give it a 1. All right, so now we can go ahead and start building simple circuits, right? Much like lab 1, I can just throw a switch in here, throw some VCC, throw on a ground. Ta-da! So what happens if I put a 1 here? Someone that's not you. What happens if I put a 1 in? Yeah.
Closes and current will flow.
Exactly. It closes and current flows. What does that mean? The output, O is a terrible variable. We'll call it Z to switch it up. What does Z become?
A 1.
If current is flowing, if this is a closed switch, it's connected directly to ground. And it's 0. Another way of drawing this, when a 1 is here, is this. Because a 1 closes the circuit. Because there are no components between ground and Z, Z must have the same voltage as ground. Any wires that are connected together that don't have a component in the way are connected together at the same voltage. So therefore, this, a 1, makes a 0. A 0 at the input does this. Now what, Z? 1. Because this is what we call RPU, or R pull up. Its job is to pull up the voltage. If the switch isn't closed and dragging it down to 0, it just kind of drifts up to on. It is not fast. Pull-up resistors, in fact, are very slow. They are not good technology, but you guys would know if you had one NMOS and a resistor, you could build an inverter. Now, for reasons outside the scope of this class, you can also build an inverter with PMOS, but it has to look a little bit differently. Okay. So this is now a PMOS device. If I put a 1 here, what does it do? What does this device do? You guys be loud. Open. So normally on an NMOS, a 1 closes it, so a 1 opens it. If it is open, unsurprisingly, this guy is called RPD, R pulled down. And its job is, if the PMOS device isn't closed, right, if it's kind of just an open floating there, is it pulls the output voltage down to 0. So if I put a 0 here, I've closed the device and I get a 1. Ta-da, inverter. Now, let's go further. I like NMOSs. This is kind of like a thing, an issue with electrical engineers, especially undergraduates, is we tend to like NMOSs better because we like to think of what we call active high. Meaning if it's 1, it's on, right? So that's active high. Active low means a 0 turns it on. We don't think as well that way, which makes us kind of dislike PMOS devices. Historically, PMOS devices tended to be a little bigger too. It kind of depends on your technology, what you're building in now. So I can no longer just blanket statement that. But because we like NMOSs, I like NMOSs, let's go ahead and build an AND gate, right? That's what we want. We want to build gates. I built an inverter for you. Let's go ahead and build an AND gate. All right, so what happens? Well, if A or B are off, we can't see the ground. We can't get there. Therefore, we must be on, right? Is this an AND gate? Draw the truth table for me. Just make sure. Think about the circuits, what the switches are doing.
So just to be sure, so when we have our inputs on, that means our switch is closed, right?
Yeah.
So when A and B are both high, yeah, and that means C is shorted to ground, right?
Yep.
So this is an AND.
Correct. All right, I'll walk you through. I like giving you guys a moment to think about it. All right, so let's go ahead and say the AND condition. That's a good place to start. If I have A is on and B is on, 1 and 1, that means this switch is closed, connected. This switch is closed, connected. There is nothing between C and ground, therefore C is 0. In any other case, we have no hope of seeing ground, right? Because if we block it at either A or B, it just doesn't reach it. Therefore, it gets pulled up to on, 1, 1, 1, in all other cases.
So if both switches were closed and there was a larger resistor closer to ground, would it still turn to ECC?
No, it would find an equilibrium point,
Okay.
which would be kind of like an, as far as our switches are concerned, we don't know. And actually, this is a good opportunity to bring this in. So our devices, NAND gates, AND gates, the things that you're going to build in the circuit, they have a sort of memory to them. So if you look at the circuit and you say 5 volts is on and 0 volts is off, right? What is everything in between? Well, it would be bad if 4.99 volts was 0, right? So we'd like to think that this midpoint, it just magically switches to the other one no matter what. But electricity is not really that clean, so it's going to kind of waver and toggle back and forth. But we're kind of saved from that because that would be really bad. If we ended up in the middle thing and it just kind of back and forth, it would light on fire or something. What really happens is it remembers what direction it's coming from. And so in order for it to go off when we're high, we have to come down to some changeover voltage. But that is not the same voltage if I'm going back on. So there's actually a region in the middle that the state of the switch depends upon the direction from which it came. So we don't like this ambiguous. We don't like the ambiguity. Now, the reality is, these aren't perfect switches. They do, in fact, have some amount of resistance. So it's kind of like having a resistor down there. Fortunately, they're just very small from this compared to the size of resistor that we use up here. So we do have to have the right size of resistor here. Otherwise, we can kind of end up in ambiguous land. Okay, so for OR gates, we don't want to be in series. What's our other option? Well, talked about this day one. We have series and we have parallel. OR is kind of like the anti-and, so it turns out we use parallel switches. Which makes sense, right? We want multiple ways to get to 0 or multiple ways to get to power. That's what OR means, either way. Okay. All right, so now, if I use this as my out, you'll sometimes, a lot of times, actually see it VO. So the O is output voltage, VO. Now what you'll notice is if I have A or B on, I have a path to ground. Once again, please write me a truth table for this device and tell me what it actually is. Is it an OR gate? Thinking about what the switches do. Okay, so if A is on, we have a path to ground. If B is on, I have a path to ground. Therefore, if A or B is on, I get a 0. What device is that? NOR. It's a NOR gate. Exactly. Okay. If I wanted to turn these, this NAND, that NOR, into an AND and OR, what could I do? What is the most like brute force blunt way we have of doing that?
Just another NMOS with our gate being V out.
Yes,
That kind of-
exactly. You feed V out into an NMOS. You can also do this with the PMOS, but let's do an NMOS. Boom. This is now our VO. We have an AND gate, right? Because this is an AND, this is an inverter. An AND gate plus an inverter is an AND gate. This is the heart of the reason why we like NAND and NOR gates, is because it takes fewer gates, less area to build NAND and NOR than it does to AND and OR. Now, part of your assignment is going to be turning this type of thing into a 3-input AND gate and a 3-input NOR gate, and thinking about what that means. All right, so let's go ahead and build ourselves CMOS, right? We've done NMOS, we've done PMOS. Let's build CMOS. Now, the reason that we like CMOS is there is a characteristic of circuits that you will learn a whole lot about in 1270 that basically says that there is a relationship between the size of the resistor and any capacitance. Does anyone not know what capacitance means? Great. So there's a relationship between resistance and capacitance and the speed of a circuit. Now, as I mentioned, NMOS and PMOS devices are not ideal. They actually have a fair amount of capacitance. And that capacitance gets bigger the bigger your circuit is. That's why when you hear Intel bragging about their 7-nanometer chips, right? Because 7 nanometer is smaller than 14 nanometer, which is smaller than 180 nanometer. And the smaller it is, the lower the capacitance and the faster they go. Now, the issue is, if you remember, I said these resistors kind of have to be big in order to work. Big resistors take up room, which is expensive, and they're slow, and they consume something called static power. So there's two kinds of power consumption in your circuit. There is static power and dynamic power. Static power is what happens if it's just sitting there. And dynamic power is what happens when you're switching, when you're toggling on or off. What you'll see is if, let's say, A and B are both open. So this resistor is tied to VCC and going into another circuit. What that means is current will be constantly flowing through that resistor. And if current is flowing, we're consuming power. It's the same issue of like if you leave, especially older microwaves plugged in, is they just suck up power when they're just sitting there. A lot of it, actually. Newer microwaves have much less of that issue. So what we want to do is we want to reduce this static power. We don't want to be consuming power when we're just sitting there. So wouldn't it be nice is if we just had two switches and never sat there just in a constant on state? We do that with CMOS. Pen's kind of giving out on me. There we go. The I similarly is Vn. I'm going to be switching through some notations sometimes just so you guys see a variety of them. But let's look at this and see what happens if it's a 1. That means the NMOS is closed, right? That means this bottom switch is closed and V out is connected to ground. I'll draw it because it's helpful. So the I so this Vn is controlling two switches. If it's 1, the NMOS closes and it gets pulled to 0, and we have VO right here. VO is 0. But as we sit there, unlike in the other case when we're using a resistor, there is no continual current. Neither in the other case, right? So if we flip this open and close, what we really end up with is there's not kind of any undesired power drain, especially if we plug into other CMOS circuits, because all they see is the gate of a device. They will never see a resistor. And that's critical, because in an ideal world, these gates of these devices don't allow any current through them. So as long as I don't have to plug into something with a resistor over here, no static power consumption. Now that's not true, right? Nothing is really ideal. These circuits do leak, and if you go to like an Intel talk, which they'll do like up at the University of Utah sometimes, they'll talk about one of the issues around like 7 nanometer devices is it actually gets really hard to isolate the gate from the rest of the FET. And they do start getting what they call leakage currents, like in substantial numbers. These have leakage. In this class, it's 0. So that's good. We like 0 currents in there, right? So that is a CMOS device, CMOS inverter. But we can do the same thing with NAND gates and NOR gates. Let's do it. Okay, so we know on the bottom stays the same with the NMOS. And we'll call this section our pull down network. has a series of logic that if you manipulate it in the right way, say A and B, then it pulls it down. Similarly, we're going to have a pull up network that meets in a different way, right? Behaves a different way. And you never want to try pull up and down at the same time, or you light it on fire and destroy the device. So we want it to pull up if and only if we're not pulling down. So pulling down in a NAND gate, right? So I'm building a NAND gate now. Happens when they're both there, right? Only in the final row of that truth table do I want to pull it down. If I'm not pulled down, I want to be pulled up. So we want to build this kind of pull up network. Okay, well, what does that mean? I want to pull up if I have, and this gets confusing because we're a PMOS device, right? So we're going to use PMOS for our pull up. Basically what it's saying is if I have a 0 in either case, in A or B, if I have a 0, pull it up, right? That's the difference between off and on, is the presence of at least one 0. Okay, so that means if we want A or B to pull it up, we want to put it in parallel. Oh, well, that was, no, we'll do it this way. And then I just have to connect them. Well, let's put A there and B is going to kind of wander over. This is a really bad way to implement it, but there we go. Remembering that if A or B is a 0, it would close the PMOS. And if the PMOS is closed, the out gets pulled up. And there we go. And you can do essentially the same thing now for NOR gates. And you can start seeing NAND gates and that kind of thing. I'm not likely to ask you something like, on an exam, I'm not going to say something like, design me an XOR gate. But I might ask, after putting a circuit up, you to draw the truth table and identify the device given this kind of schematic. So be able to understand what happens when you place a value at the gate of one. I'm not going to worry too much about the knowledge of the source and drain, but be aware of the gate because that's a really common vocabulary word I'm just going to use. So the gate, if you put a voltage at the gate of an NMOS or PMOS, be aware of what it does. The next most important thing that you just kind of have to trust me on until you get further in device physics is the NMOSs go on bottom, the PMOSs go on top. You can't put PMOSs down here. Now, the reason for that is you have a hard time, well, an impossible time creating the conditions voltage-wise in order to make PMOS work when they're down here. They kind of need to be biased more towards the positive voltage side. That's something, again, you'll get into in later other circuit classes. I don't want to bog you down. Just be aware that your standard structure looks like this with NMOSs as a pull down network, PMOSs as your pull up network, and they have some relation between them. And I could have, let's say, a series of questions. Let's say on an exam, let's say I put up this one, that one, and the third one, and I would ask, draw me the truth table, what device is this, and is this a viable device. Now, what I mean by that is, does it work? Keeping in mind you can only either pull down or pull up. If I show you one that does both at the same time, it doesn't work, because what is the value if it's pulled up and pulled down? We don't know. We also don't know if what it is if it's not pulled up or down, right? It's just something. Sweet, we've done good. Are you guys doing okay on this information? This was kind of a flurry of it. Do you have any questions on the material so far? Okay, this is the second time I've given this lecture this week, or well, I actually did on Thursday, but so sometimes it goes faster the second time I give it, but it also tends to be a little clearer. If you start struggling, let me know so I can slow it down. I'm about to then teach you a new tool in the analysis of circuits. Now, truth tables are massively valuable. If I get stuck in my algebraic simplification, I do just bust out a truth table most of the time because they're so direct. But there's another type of tool that we need that kind of captures the dynamic sense of a circuit. Because circuits don't just sit there and stay the same, we want to see how it kind of marches through that truth table. So let's start with a simple one. Okay, so what this circuit technique is designed to do is help you view the process of how the signal flows through the circuit. And it's called a timing diagram. And what it's going to do is it's going to have one row for each input and output. But we also like to assign values for intermediate stages. And what I mean by that, so is like here and here are kind of intermediate stages. So let's just call ahead and jump to the end of the alphabet for these as X and Y. At our output, I'll just stick it F so that everything is far away from each other in the alphabet. So as I said, I want one row for each of the variables, inputs, outputs, and intermediate stages. And then I'm going to go ahead and just, this will make more sense later. I just kind of assume a rate of change for these. So what I want is I want to see A do the following. It'll go 0, 0, 1, 1. And I want B to go 0, 1, 0, 1. Okay, so I'm just going to assume there's a rate of change because I don't want to do this. That doesn't really help us view anything, and it doesn't really help. So as I said, A starts at 0, low. It then goes up, or it stays 0. I'll just do some, actually, I'll do it in a different color. Okay. They're both dying. That's too bad. Okay. So it goes 0, 0, it then rises to 1, and then stays 1. B also starts at 0, rises to 1, falls back to 0, rises to 1. So this is just saying that in time, A is changing and B is changing. Now we can use this to analyze what the rest of the circuit is doing. Okay, so during this first period when A is 0 and B is 0, what is X? Well, X only cares about what A is doing, right? So another way of writing X is also just saying not A, which means I look at A and just do the opposite of what A is doing. So if A is 0, X is 1, and if A is 1, X is 0. Okay, now Y. Y is equal to A and B. This one's a little bit more complicated, right? I need to look at A and B and evaluate them. An easy way to do this with, let's say, AND operation is I can just say, well, I know if A and B are 1, it's 1, otherwise 0. The only place that A and B are both 1 is here. So this is 1, this is 0. Okay, now F. F is going to bring all of this together and could be complicated, especially if we have like a 6-input OR gate. But I don't have to worry about that. All I have to worry about is the fact that F is equal to X or Y. So I can forget about A and B right now, and I can just look at X and Y. And I say that F is true if either of them is true. So starting out, X is true. Still true. At this point, X drops to 0, and Y is still 0, so I don't have X or Y, but I am going to get Y back. Feeling good? Make sense? That's timing diagrams. You will see lots of these. Later, maybe today, I'm going to introduce VHDL, like for real. I've talked about it before, but I'm going to start talking VHDL. And then when you start getting into labs for it, you're actually going to be using and creating timing diagrams based off of your circuits. You're going to build the circuits and it will make the timing diagrams for you. And the timing diagrams are how you're going to be able to tell if your circuit is working. Because you'll have a circuit that you'll think says, okay, so it says, it's supposed to say that if X or Y is true, then it's true. And you might see a circuit that does this, your timing diagram, and you'll go, oh, something's not right. So understanding these timing diagrams is really at the heart of being able to fix your circuits when you inevitably program them wrong, because you will. Does anybody want me to walk through the timing diagram on, say, we could do the mux, or do you feel okay? You feel okay? Oh, you want the mux? Okay, let's do the mux. I'm gonna leave A, B, and C. So let's go back and remind ourselves of the mux equation. Let's call it M is equal to S bar A or S B, right? That circuit then has an OR output gate, two input AND gates. And let's throw a hitch in there. Let's say that I tell you that you are only provided with the non-inverted inputs. What that means is you have S, but you also need an inverter on one of these. Okay. Let's go ahead and call this one X, this one Y, this one Z, and this F again. So now I'm going to go ahead and add another row. Eventually you'll feel okay skipping some of these rows because like this X is just not S. But we, how do I phrase this? We don't want to get lost. It is still helpful to write them even if they're simplistic, especially as you're learning this. I recommend against skipping. So we know that X is just equal to not S. Y then is equal to A and X. Z then is S and B. And then we'll deal with F. I don't want to have it in there. Okay, and now you've got to be provided with something usually. But let's say that I just told you, I want you to, sorry. I forgot one row, which was S. Right, I forgot that input. So let's say I tell you that I want you to thoroughly test this circuit. If I want you to test all possible inputs, that's what thoroughly test means. Thoroughly just means all possible input combinations. And in fact, if you're getting really thorough in industry, you test all possible input combinations with all possible directions of switching. We won't worry about that. But we're going to have 2 to the 3 possible input combinations here, right? Which is hard. That's a lot of numbers. I mean, that's 8. But if I had 4 or something at 16 combinations, it gets a lot. So let's just say that I want A all right. So A, I'm going to do something simple with. It's going to start 0, and it's going to go 1, 0, 1, 0. B is going to go 0, 0, 1, 1, 0. And then S is going to go 0, 0, 0, 1, 1. So this is something that you would likely see on an exam style question of this, where I would say, given A, B, and S in this picture of a circuit, finish the timing diagram. All right, let's finish the timing diagram. Well, X is easy because it's just not S. Great, right? I'll step aside and give you guys just a minute to do Y, Z, and F. if you guys get stuck in the middle of one of these exercises, you can ask me to come over and I'll answer questions so that you don't get stuck while just staring at this. Because I do want you to have this as an opportunity to learn. Okay. So now let's start looking at this as y, right? Y is just a and x. So I can look at these two, they're spaced out a little bit, and I just need to identify any locations where they're both true. So here, I think is my only one, right? Because there's the other time that A goes true, but other than that, it falls. So that's it. And then Z is S and B. S and B. So here's S and here's B. This is their only window where they're both true. Everywhere else is 0. Okay, and then F is just either one of those, right? It is either Y or Z. So no, yes, no, yes, no. Oh, good? Great, okay. That means with plenty of time left on the clock, and we still might get to finish early. Are we good if I start erasing? Okay, I just want to make sure I can erase. I just hate to steal that away from people when they're still copying something down. So I've been priming you for this lecture since day one, which you guys haven't been here that much, so who knows how much it did. We're going to talk about what is VHDL. VHDL is a hardware description language and HDL. There are two different types of HDLs that are really common in use. There's more than that, but we use two primarily, VHDL and Verilog. We teach VHDL here because the majority of our graduates go on and work for either government or government contractor. It tends to be true in the US, VHDL dominates the defense contracting. Verilog dominates industry outside of the military industrial complex. And I mean dominates. I've never seen it inside a company outside of military. So the benefit is, it is almost universally agreed that if you know VHDL, learning Verilog is a cakewalk. The other is not true. I learned Verilog and learned VHDL, and it was easy, and I'm not a strong programmer. They're easy. If you know one, you know the other. The hard part is understanding how to make it work, because you're not programming software, you're programming hardware. You're designing things that don't have any obligation to go in order. In a program, if you're writing in C++ for your computer or Java or whatever, it has a scheduler. It does this, and then it does that, and then it does this. Now, this has its pros in that you just kind of write your code and it happens. It'll get around to it. VHDL is basically intrinsically optimized for speed. It's very fast. For perspective, one of the times that I was trying to design a circuit, all I was doing is I just needed an input that was really a binary counter. It had 4 outputs, and one was just going 0, 1, 0, 1, and the other one was going 0, 0, 1, 1, 0, right? Just counting in binary. I was using an Arduino. It had a clock speed of 32 megahertz. I was able to switch that lowest speed at 20 kilohertz, maybe. I was really pressing it, and it wasn't even, because what I would have liked is this. Like, this is what we would call like a clock signal, right? Low, high, low, high. It's just counting. It's a clock. This is a digital clock. Now, what was happening was the scheduler was like, I'll get around to it. I'm busy, right? I'm talking to the PC and I'm thinking about the numbers. And so it would do stuff like this. Oh yeah, I'm supposed to be a 1. Oh wait, I'm a 0. Oh wait, no, I'm not. Okay, here we go. And it was just not good. In VHDL, if you tell it to do this, as long as you don't screw up, it will do that. It's really predictable, it's really handy, and they're really fast. And I was able to do on a FPGA with a 1 megahertz clock, I was able to generate a 4 megahertz signal. They're just better. They're reliable, they're fast, but they're harder. So if you see me designing something and it has like a GUI or a graphical user interface, GUI, I will almost always use a processor because that's too complicated of a thing to easily design on a digital logic. But something like that, it requires number crunching, math. Digital logic dominates the world in that. Okay, and all processors are just built out of digital logic. In fact, you will learn how to build a processor by the end of this class. All right, so now that we kind of have what VHDL is, there's a couple of terms that you're going to hear that you need to know. So one of them is called schematic capture tools. What that is it basically gives you pictures of AND gates, and then you drop them down into a schematic on a computer, right? So it's software, and you wire them together, and the circuit does what you think it should do. The downside to this is we know that this AND gate, now that we've done it, takes 6 transistors to make, right? Each NMOS or PMOS device is called a transistor, takes 6 of them to build an AND gate. Pick a chip in your phone, open it up, look at the little green board. Each little chip in there has millions of transistors. You are not going to sit down and throw down millions of AND gates in schematic capture. I have yet to, it doesn't mean it doesn't exist, but I have yet to meet a company that uses schematic capture. I haven't seen it. I don't teach it, but you need to be aware of it. And part of what it does is a benefit to you guys that you're gonna miss is it helps you visualize what your code is doing. But the code is what matters. So I will do my best to make sure that it's clear what your code is doing and how it relates to the pictures we draw. So if we were to draw this circuit, the nomenclature for this is A and B are what are called, well, and if we call this, are all what we call ports. Ports are the inputs or outputs to some form of logic. Now, another way that you'll hear me describe schematic capture and is an immensely powerful tool for planning is called the block diagram. So what you'll see in a block diagram is, let's say that I want to build a circuit that adds 2 binary numbers together. I know that that port needs an A, a B, and the sum of those. Now, we'll get to why, but it also has another port that we call the carry out. What that carry out is the carry of a mathematic operation. So if I do 7 plus 5 and I get 13, if I only had 2 bits, right? So I'm adding 1 bit and 1 bit, I'm gonna have a 1-bit sum. I don't know the difference. So this is the decimal approximation, right? If I only have 1 column to store that in, the 1 disappears. So the carry out is just the next column, right? It's just carried over. So if I have a 1 and a 1, it lets you know. Okay. So let's say I have A, B, S, and CO as my ports. I would then just call this, sorry, I'm going to redraw this so it's a little bigger. I would call this adder. So what this means in terms of a block diagram is that I know that inside of the adder is just adding A and B and outputting S. Now, if it was more complicated, you'd have to provide documentation. And you will see something like this if you take my 3610, where you might see something like I could have a USB block. So USB has a differential data signaling, a plus and a minus that comes out. Older USB anyways. It needs a clock signal because a lot of stuff that we'll learn about later, we're gonna start off not clock, but later we'll need clocks. And then it takes S data. S data usually means serial data. It means it takes 1 1 at a time or 1 0 at a time. And then it turns it into the USB packet for us and we send it on out. This would be an immensely complicated piece of logic to design, but we know what it does. And this is what you'll be tasked with for reals as an engineer, is they'll come to you and say, we want you to build this block. It's gonna take a clock, S data, and a plus and a minus output. We don't care what happens inside. Make it. That's the kind of specifications you'll get a lot of the time. So when I say block diagrams, this is what I'm talking about, is the block level thinking. And then you're gonna like connect them together with wires. So like say that this clock, USB, just wanted to continually send whatever the sum of the output of that adder is, they're connected together. Ta-da. You're gonna do this in code, and I will try and carefully walk you through how that works, starting now. So the first thing that I need you to understand is sometimes, in fact, most of the time, I'm going to be writing at some level of what we call pseudocode. What that means is I will try and convey the idea of what the code is doing, but it's not going to be perfectly syntactically correct. If you put it in the computer, it's not necessarily going to run, because I'm going to have a tendency to forget semicolons. That if you're unsure, you can ask me and I'll try and puzzle it through. I rely more on the software tools to make sure my syntax is correct than maybe I should, but I don't have a job that I sit, 8 hours a day programming VHDL. I do a lot of this, so it's hard for me to remember. But let me take a drink. Sorry, I'm running out of voice. I don't think VHDL is that hard of a language. It's kind of nice. It just has a few quirks. So let's start by just talking, what does VHDL code look like? All right, so the first thing it has to do is it has to have what we call an entity. And that really is the block that I just drew, right? So that adder would have an entity. So we do this by just starting, and this could be your first line of code. Entity. And for today, I'm going to try to be perfectly syntactically correct, but I may miss some things. The books have perfect syntax examples. Okay. Then it needs a name. This is what, like, the adder was my example, right? Actually, I'll leave it up so I can kind of point to things. Okay. So I need to say that my adder exists. This is its entity. But I'm not going to do the adder because the adders come later and they're kind of complicated. So I'm going to stick to something simple, and I'm just going to call it example. and VHDL is annoying and it makes me put in is. And then I let it know what the ports are. So in the case of the adder, it would be A, B, S, and C, O. This case, we're just going to do a simple logic operation. I'll put it up here so I can point it out. I want where F is equal to X1 and X2, or X2 bar and X3. So I just want an entity, a block that does that. Okay, so my entity example is, it has ports X1, X2, X3. Sorry, I keep trying to write them as subscript and they're not in this case because it's code. Okay, but then I have to tell it what are those ports. And this is just for error tracking. What belongs on those ports? What type? Well, they're bits in this case. And the other thing I have to tell it is what kind of port is it? In this case, it's an input. In. So X1, X2, and X3 are inputs, and they are, oh shoot, sorry, bit, not bits. Okay. I then put a semicolon here. I'm not done, I haven't closed the parentheses, but just for the keeping the code clean, this is a really nice way of doing it. I could do it all on the same line, this is better. Okay, F. F is my other port because I need an output. It too will be a bit. Shoot. I think this needs a semicolon, but I can't remember for sure. And then VHDL loves ending lines with semicolons, except for when it doesn't. It's really obnoxious in that one sense. You'll notice there is no semicolon after the is, but it's kind of everywhere else. Okay. In and out, we call mode. Bit, we call type. The other things we call ports. Okay. Now, this is just telling the outside world stuff. That's all this is doing. This is doing no thinking for us. This is just telling the higher levels, the upper things, what the block diagram looks like. What ports is it looking for and what things should I be attaching to them? Bits in this case, okay. Now it needs an architecture. That is, what does it do? The architecture needs a name of its own. Don't put too much thought into them. I'm just going to call this one COM for combinational. So what combinational means is we're building combinational logic. There are really two major classes of logic that we will build in this class. The first is combinational. The second is sequential. Sequential is more obvious what it means. It means it does it in sequence. It does this, and then this, and then this. Combinational means it just all happens, all at the same time, like a circuit. Okay, then I say what the architecture belongs to, and that it is a thing. So the architecture, named combinational, of the example block is, here I have to give it the begin keyword, and this is where VHDL gets really nice, if a little bit weird. When we want to assign something, we don't get to just use equal. We use this symbol, which basically is saying that whatever is on the right side of the equation is getting put into F. if you use just equal, A equals B, this is not an assignment statement. This is a question. It's asking, is A equal to B, and will return true or false, 1 or 0. This is an assignment. There is one other form of assignment that you will see. We'll come back to it later, which is this. Put that on your mind, forget if it exists. It's bad. This is our assignment statement. I just want you to know, if you see the colon equals, don't freak out, because it does work. It just has some quirky characteristics that we'll capitalize on later. Maybe you may have to take 3610 to really understand that one, but all right. Now, to execute this is pretty easy. I just say x1 and x2, or now, VHDL is not case sensitive. There's one exception that I'll get to at the end of the semester, but for now, just assume that VHDL is never case sensitive. However, it is best practice when you're using keywords, which means things like and, or, begin. Actually, I never do on begin for whatever reason. Out, in, bit, those kind of things, to just put them in all caps. It makes them stand out. It makes the code easier to read. This guy does need a semicolon, and this whole line, its vocabulary word, is an assignment statement. We are assigning F to the things on the other side. And notice I just write the words and. I don't need parentheses for this not, because not takes precedence in the order of operations, right? So not is the most important thing that it can do. It will always not first. And, however, happens before ors. Multiplication happens before addition. So in order to get these ands correct, I have to add parentheses there so that we're clear. When we handwrite it, it's kind of obvious. This doesn't really know, because we can't just write x1, x2. We have to say x1 and x2, parentheses. Okay. Then I say end the name of the architecture.
Yeah, sorry. I just wanted to clarify. So where our last part of that assignment statement, could we write x3 and not x2 and still have the same?
Absolutely.
Okay.
Yeah, so this is the first thing that will happen no matter where it is.
Oh, okay. So.
Yeah. If you wanted not x2 and x3, you would need parentheses. Right, so that would be x2 and x3 all barred. Okay. Now, as I said, this is combinational logic, which means everything happens at the same time. And I can branch this out. So I could expand the ports to say that I have. Are you going to hate me if I go back and edit this? Because I know your notes are going to be nice and clean. They'll ruin them. Is that okay? I don't want to do a bunch of writing. Again, I keep writing freaking. Okay. Now I have two outputs. And let's say I want my F2 to be a mux, where X1, let's make X3 select. So I'll write this out. So X1 is mapped to A, X2 is mapped to B, and X3 is mapped to select. Right? Okay. I'm not going to add any more ports. I'm just going to keep in my head what those are doing. And we knew what that equation was, where it was select, not select A or select B. And I would write F2 then gets assigned to this. Not X3 and A, which is X1, or X3 and X2. All right. So let's say that I want to complicate this. And I only want the mux to function if F1 is true. So I add another parentheses. All right. There's a couple things for me to disentangle here. So first off, F1 and F2 assignments will happen at the exact same time. And we're actually can run into some issues with that because it's not like F1 then F2, it's simultaneously. That's what the combinational means, simultaneously. Later, we're going to build out what we call sensitivity lists that will they'll only evaluate these statements if something on the sensitivity list changes. So you could say something like, I only want to do these assignments if X1 to 1 or 2 changes. X3 can toggle around all at once, but I'll only change if X2. But if X1 or X2 did change, you would evaluate both of them at the same time. And we'll get into later how this causes errors, because it does. If you're not careful, it causes some problematic errors. But keep in mind, these happen. Now, the next thing, this sounded like a good idea, right? I was like, okay, I only want F2 to be true if F1 is also true. However, VHDL doesn't like you to put F1 and output on the right side of an assignment statement. This will actually cause you an error because of that. What you can do is you can assign a different value to F1. I'll save that one. Keep this in mind. I'll walk through the right way to adjust this later. I don't want to bring it out yet, but I do want you to be aware VHDL hates having an output on the right side. The quick and dirty way of doing this is there is a third type between in, out, well, third mode called in, out. And it's both. It is both an input and an output, and it can go on either side. That is one fix. I will go over a better fix at a later date. Okay. 64. Yeah.
Will it like freak out if we put extra parentheses or?
Not at all. It's totally fine. Also, thank you for asking that. The HDL has no requirements for formatting. So you've seen how I've kind of done these tabbing. If you learned Python, it's going to be helpful because I recommend just using the Python standard formatting. What that means is tab things in when they're different, so it's clear. Because it doesn't look very clear if it's entity port F1, right? It's hard to tell. When you tab things like this, I can go entity port, okay, this is all of my port stuff, and then the next time something comes back, it's tied. So this entity is tied to that end. This end is tied to that begin because they're at the same level in tabs. Use your tabs, they're your friends. More than that, they're my friends. If I come over to your desk and you're in the lab and you're trying to work on a project or lab and your code looks like this, I will happily help you. If I come over to your lab desk and your code has no tabs, I'm gonna look at that and go, fix the tabs and I'll come back. Because I'm not gonna read your code, because I'm not gonna get it right. And in fact, most of the time when you fix your tabs, you'll see it. Tabs are important. I can't underestimate that. And literally when you get to any of the labs or assignments that have code, that's part of your grade. It's just tab. The code will run without, but I'm not gonna grade it. All right. 61 is a page that is a little bit helpful in that it talks about the design process for making digital circuits. So the first thing that we do is we gain the design conception. That's the idea of the design. What are we trying to do? So think back to our light bulb example, right? So I could easily give you an assignment after today that says, write me some VHDL to implement the light bulb example, the light switch example. That should be within your skill set. Now you couldn't simulate it, and maybe it wouldn't be quite right, but you should be able to write code that approximates that. I'm not assigning that, but I could. So that's the conception, the idea. The next is kind of deciding on your entry. And this is where you decide between just VHDL or schematic capture. Now this book is gonna walk into schematic capture. I'm pushing that aside. We're doing VHDL because that's what you'll do for the rest of your life if you pick this job. And you'll make good money doing it. Then we have to go into synthesis. And what that means is the code has to be interpreted, there we go, into what is this in logic? Because you can actually write code that is not quite so obvious what it's trying to accomplish as far as digital circuits. You can, for example, multiply two 8-bit numbers. Now, I don't expect any of you have any idea how to design a circuit that would multiply two 8-bit numbers. However, in VHDL, you just say F1 times F2 is, yeah, you're done. So synthesis is the process of saying, what did you write and what does that look like in a circuit? This then has functional simulation. What that means is we simulate it. We run code that approximates the function of the circuit. It's not perfect. And just because it simulates does not mean it will actually work when you turn it into a product. There is a discrepancy between simulation and reality. This is true regardless of digital, analog, power, take your choice. Any simulation is just an approximation of reality. It's the accuracy of that approximation is tied directly to your ability to set up the simulation, of which we will cover. Okay. Then once you've done that, you can decide, did it work? Does the simulation look like it did what I wanted it to? You obviously would hate to go spend $1 million on a chip, get it made, and find out it didn't work, unless you at least had something saying that it probably will work. It can then take into physical design. What the physical design, word's leaving me. They use physical design. The real word is, shoot. Sorry. Implementation, I think, is the one that they use. What that means is, we've talked about universal gates, right? NANDs and NORs. So first it turns it into logic. And then the next step is it turns it into hardware simulation. It makes it try and look like what that final product really is going to be. So synthesis might have AND and OR gates. Implementation is going to have NAND gates or NOR gates, whatever your actual product is. Some technologies do use multiple kinds, but it will translate that into a real thing. Then you can do post-implementation simulations, which then further more accurately approximate, because it starts taking into account device physics. And then you can start going on to what they call timing simulation, and that accounts for the physics to determine if you're going to work. When they have those timing diagrams, we use ideal timing diagrams, but there's a real thing we call delay, where you tell it to go one, but it takes a little while, and then it goes one. You can simulate that, but it takes a while. If it works, then you could go on and actually like configure the chip and make it. Yeah. Okay, sorry. Puzzling through, I'm just about at the end here, so we're gonna get to go a little early. I just wanna make sure I haven't forgotten anything. Sometimes I do that. Da, 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 da. Okay, yeah, so I think that's actually all I need to cover for today. For this, you'll start seeing some VHDL in your assignments this week. That's just gonna have you start writing some really basic code. You won't be simulating it, it's just kind of to get an idea for it. And then next week, my goal, and may take till the week after, it's always a little figuring it out. I'm gonna try and bring in, I'll bring in my laptop and I will actually show you guys the design environment that we're gonna be using. It's called Vivado. It is a free software program. It is large. It is available on the lab, but you can install it on your laptops or home computers, whatever to do wherever. I have something posted inside of the files inside of the lab folder called Lab 0 that is a walkthrough on like the right way to install Vivado. It was designed for juniors, be aware of that, but it's fairly straightforward if you're comfortable with computers. Be aware, engineering software tends to have more glitches than consumer products. Just partially because there's less users, partially because they can get away with it. There are some terrible bugs that you run into, and you will find yourself closing Vivado and reopening it to fix some of them. If you're having just inexplicable bugs, I recommend doing that, just to be aware. We're gonna learn about like the types of warnings you'll see, how to code, how to simulate. We'll walk through all of that, I hope, next week. I'll hang out for a little while if you guys have questions. These night classes, because we actually have a little bit longer than the day classes do, because you don't have that break in between classes. So a lot of times what I'll try and do is I'll give you 15 to 30 minutes at the end to just ask questions if you're curious. And that can include either homework questions, material questions, or job-related questions, degree or oriented questions, that kind of thing. So. Yeah.
Sorry, are we good to move into homework questions right now?
Yeah, absolutely.
Okay. So what does it mean with the minimum sum of products or the product of sums? Is that just the Like the
Yes.
sigma little m notation
Yeah.
or?
So this is well, no. So the min terms are one thing. Then the minimum sum of products is this for a mux, right? So we have a sum of products that we get directly from the min terms, but the minimum sum of products is this. And why that matters is what I don't want. So let's say I had something that was like this. I don't want that, because that's not a sum of products.
Right, that's.
That is. So it's what it does is it makes sure that you all get to the same simplification, so my grading is easier. Because right, that feels simpler, but it's not the same visually. It is the same functionally.
So what did you say about like this is like degree relating like directly a lot to the military industrial complex and stuff like that?
Oh, that's just VHDL,
Oh,
the
VHDL.
language itself, not the degree as a total. So the degree as a whole, most of the students do get employed by Hill Air Force Base, Northrop Grumman, L3, and those. That's just the bulk of the employers in the area. Far away from the only employers in the area. Because some people get excited because, right, there's two sides of it. Some people go, yes, I want to build missiles, right? Because that sounds cool. So like one of the jobs I turned down after I got my master's degree was designing, so for Northrop Grumman, they wanted to help design anti-ICBM missiles that were just buoys. They were just going to drop these big buoys in the ocean, and they were going to be able to launch missiles to shoot down incoming missiles, right? Cool project. Myself, I've worked for L3. I worked for that. I don't like the red tape that comes with government contracting. At the same time, I worked for a neurotech company designing implantable medical devices that there were like 30 people in the company. There was no red tape. There was no organization, and I loved it. It was madness, but had nothing to do with military. All of the money came out like NIH and stuff, that National Institute of Health. So when it comes to the major, take your pick. Electrical engineering is probably the most diverse major as far as what it comes to where you can get a job. It's just VHDL is a language specific to our government. But as I said, you can just learn Verilog if you want to go work for non-military. So when I was working for, the company was called Ripple Neuro. When I was working for them, they were all Verilog. Not an issue. It was not an issue jumping back and forth between the two. So you're equipped either way. Don't worry, you're not like getting locked into one thing in the major. And even more than that, you could go, I mean, I turned down a job from Goldman Sachs because they like hiring engineers to be technical consultants. They don't care what you learned as the EE, they just want your ability to analyze and learn. So no, the major is incredibly flexible. VHDL is a little more constrained, but what you're learning is the skill set that will help you a lot. Answer your question? I'm kind of wordy. Anyone else? Yeah.
So our homework was due the 20th, right? The first homework.
Probably.
And so I noticed I mixed up on the max part. And so if I were to.
If you want to fix it, go for it.
And then just put it in the same one, even though it's past due.
Sure. I'm pretty lenient on the deadlines for you guys for this class because COVID is chaos. The point of the deadlines is for you guys to not fall behind, because while I will allow it, it's really hard to make up the whole class in a week, aka impossible. So don't worry, you can fix it, you can turn it in, you'll be okay. Yeah, I realized that I needed to recover that one. So yeah, thanks for asking. Cool. Thanks for coming, guys. Have a good night.